And so today we are going to start with one of our members of our DinAmicI group, Stefano Marò from University of Pisa, and we will talk about chaotic motion in the breathing circle billiard. And so I remind you that this video will be recorded and broadcast online on YouTube. So if you speak, you accept that you will appear in the video. Okay, so Stefano, you can start.
Okay, well, so if everything is fine, I would thank Alfonso, Marco, Claudio, and all the DinAmicI staff to have invited me to give this seminar here. And well, what are we going to talk today? We are going to talk about the so-called breathing circle billiard. And let's start just saying what it is. So we are studying the dynamics of a ball that is moving inside a billiard that is not a usual one. So the billiard first is circular, but differently from the usual billiards, it is moving in the sense that the boundary is not fixed. It is not a frozen billiard, but you can imagine it as the boundary is somehow breathing. It is expanding and contracting according to a periodic function that we will call R of t. So depending on the time in which we are hitting the boundary, then the boundary will transfer energy to the ball. So what happens here is that the ball is not moving at the same velocity during his motion because actually the boundary can change his velocity. So what we are just studying is tell something or whatever we can about the possible motion that are allowed by this for this ball. So why should this problem be interesting? Well, there are several reasons, but some of them is that actually what we are trying to do is trying to extend the well-known dynamics for a frozen billiard that is very well known. In the case of a circle, everything is well defined. We will see it later. But also, this model can be seen as a generalization of the famous Fermi-Ulam ping-pong model. So what is the Fermi-Ulam model? So the Fermi-Ulam model started with Fermi, who tried to explain the high velocity.
Sorry, there is a question.
Yes.
By Francesco. Does the boundary move only in the radial direction?
Yes, yes. It is only it will always remain a circle. So the boundary, yes, the center is fixed. The radius is increasing and decreasing. It will always remain a circle with the center that is fixed. Okay.
Yes, thank you.
Okay, so the idea is, imagine that you have this circle in your table, the center is fixed, and the circle is expanding and contracting. Okay, so we will talking about the Fermi-Ulam ping-pong model. So the Fermi-Ulam ping-pong model, what it is? So the idea was first proposed by Fermi, that he proposed the model that to explain the high velocity gained by photons, it could be possible just because photons somehow bounce between pulsating galaxies, and every time that they go circle to a galaxy, then they are shooted with some gaining of energy. But then Ulam gave a, let's say, more mathematical friendly model that is the one that is drawing here. Actually, you have two rackets that are moving periodically, and the ball that is moving between them, and the only force that acts on the ball is the force given by the impact. So the motion is free between the two balls. So the question proposed by Fermi is: can this model allow for an infinite velocity of the ball? So the question is: can you increase the velocity of the ball up to infinity, just hit with this sort of ping-pong model? And there are some results about it. So the first is given by Lederich and Levy that says that actually the regularity of the motion of the racket is crucial. Then they proved that if the motion of the racket is sufficiently regular, then C6, then there is no Fermi acceleration. So all the motions of the ball have bounded energy, bounded velocity. This is for the Fermi, the ping-pong model. Then the same result was proved by Campos and Pinto de Carvalho for the breathing circle. Actually, here the regularity is some more. So the idea is that you want to apply KM theories, and you have to put some regularity. And actually, you can imagine that these two results are strictly related, because, for example, if you in the breathing circle, a motion along a diameter corresponds exactly to the ping-pong model. So these two models are actually well related between them. Then also, beside the Fermi acceleration problem, another related problem is, okay, what can we say about the general dynamics for these kind of systems? And for the ping-pong model, there are some results, a series of results by Czarnyski and especially also Dolgopiat and Desimoi, in which they consider f, and actually there is a mistake, it is not f, it is the derivative of f to be discontinuous. So if your function is not regular, then Fermi acceleration is possible, and also there is complex dynamics, and in particular you can also prove several ergodic properties of the model, talking about the ping-pong. Going towards the breathing billiard, there are also some recent results in which it is proved that you can have Fermi acceleration and also complex dynamics if your billiard is moving, if the shape of the frozen billiard also allows some chaos inside it. So here we're talking about not just the circle billiard, the breathing circle, but the breathing billiard in general with the boundary you want. So the result here in 2012, they show that if you have chaos in the case of the frozen billiard, then this chaos can be somehow translated to the moving boundary model. But then the question is, okay, what happens if you are considering a billiard, a boundary corresponding to a billiard whose dynamics for the frozen case is regular, for example, ellipses and circles? And then in 2018, Dettman, Fein, and Turai proved that actually if you consider an ellipse that is slightly moving, always remaining an ellipse and not a circle, then you can prove that there is the phenomenon of splitting and separateness, then you can prove chaotic dynamics inside. So what we're trying to do is, in some sense, to complete this picture and say, okay, what happens to the circle? So the circle is the most simple dynamics, it's completely integrable. Then what happens if the boundary starts?
Va bene, grazie, arrivederci.
Okay. So what we are going to study, we said that since it is already known that all the motion actually for regular motion of the boundary are bounded, then we want to study bounded motion, that is motion with bounded energy. So the question then is which kind of, so what do we mean by a motion, then what do we mean by a solution? By solution we mean a function that is defined in R2 associated to a sequence of impact times. That is the time when the ball hits the boundary that satisfies this property that actually is a formalization of what intuition would suggest. That is, between two bounces we have a free motion, and the motion is always inside the moving billiard table. Then the sequence Pn are bouncing times in the sense that the solution at that time is on the boundary, and the latter here is the bouncing condition. It is actually it is an elastic bouncing condition. And what happens is that the tangent component of the velocity is preserved, and the impulse is only given in the radial direction. And here, actually, we have to change the direction, obviously, and then we add this part that is given by the impulse that is given by the boundary. Then actually with a picture, what up the bouncing condition is just sketched here. Then you have the incoming velocity is the orange one, the outcoming is the blue one. Then we have the tangent component is preserved. And what happens to the normal one? The normal one is not preserved, but is increased by this part that corresponds to the impulse that is given by hitting the boundary. Actually, this part can be positive or negative. For example, if you hit the ball when the boundary, for example, is shrinking, then you give impulse to the ball. But if the ball hits the boundary when the boundary itself is expanding, then this part would be negative, then the velocity would be smaller. Okay, so which result are we going to prove and to discuss is the following one. So for the moment, let us state it in a heuristic formulation. So we suppose that the function R2 is regular, let's say at least C2, R is periodic, the period is 1, and the result that we are going to study is to discuss is that we can find actually two classes of functions we call R and R tilde, such that for a function that is motion of the boundaries inside the first class, the class R, then we can find periodic and quasi-periodic solutions. Then we will describe what we mean about it. And if we restrict this class to the new one that is R tilde, then we have chaos. What do we mean by chaos? For the moment, just say that we can find some invariant sets, invariant measure with positive entropy of a map to describe the motion of the ball. So just a comment about this class of maps, this class of functions, actually they are defined in quite a cumbersome way, but we will see it. But what we can prove is that they are not empty, that hopefully this should be every time one define a class of function. And actually a representative can be a sinus function. So a good radius for which we have chaos and all the result holds is this one. So we have a sinus that is multiplied by times delta, then delta is supposed to be somehow small, but not too much. But what's important is that M is very large. So we have a very big, so what we have is a very big circle that is moving not so fast. So this is more or less the class of function that stays inside our R and R tilde. So just to start, let us talk about something that is very well known, that is what happens in the case when the boundary is frozen, so the fixed billiard. So everything here is well known, then the bouncing condition is just the mirror law. Then what happens is that the incoming velocity and the outcoming velocity have the same modulus, and the angle of reflection is preserved. Then a typical way to describe this motion is to introduce the variable s, that is the arc length of the boundary, and phi is the angle of diffraction. Then by standard geometry, we get that the map can be defined in this way. Then the map can be defined on a cylinder. Then the new point of impact given a first point of impact and an angle or a shooting angle, then the next one is given by this map, so the angle is the same, and we are just moving along the circle. Then this map, clearly it is an integrable map of the cylinder, and the phase space is just put in here. We have actually a cylinder, and each orbit can be recognized and parameterized by this number omega. This is just the angle rescaled. And then we have the omega can take any value from 0 to 1/2, and it, in some sense, it describes the orbits, in which sense here, it is written here. Then omega in general is called the rotation number because it satisfies a sort of average velocity of the rotation, just rescaled in this case, and identifies the trajectory in the sense that if omega is rational, say P over Q, then the trajectory is closed, and it closes after Q bounces, giving P revolution. While if R is irrational, what we have is a trajectory that never closes, and the bouncing points are dense in the boundary. Here, this is a classical picture in which we saw the trajectory with rotation number 1/5, that is the red one, is a pentagon. That is 2/5, then it is, we have, once again, 5 hitting point, but we make two turns because before closing. And this is a typical, for example, trajectory with irrational rotation number that is, actually we can see that the motion, the trajectory never closes and hits almost all the points in the boundary. Then for the future, we also know that if the rotation number tends to 1/2, then the shooting point, the outcoming angle is π/2, and then we have a motion along a diameter. Okay, so let us thus go into the coming back to the map. The map actually is very simple, but it is a so-called twist map. That means it satisfies this property here, and actually it has a clear meaning. If we want to go farther on the boundary, we have to increase the shooting angle. But on an analytic point of view, it means that we can express the shooting angle just as a function of the true impact point. This means, for example, twist is just this derivative as a definite sign. But moreover, we can also describe the map through a so-called generating function. That is, there exists a function h, that is, in this case, this one can be computed explicitly, such that the function is defined in this implicit way. And this will be very useful in the future. So this function is called generating function. And the fact that the function is twist corresponds to the fact that the mixed derivative of the function of h is a definite sign, then we can invert this relation without problem. So this is basically what is known. They say that everything is known for the frozen circle billiard. And then we can think, and okay, why don't we use this kind of variable to study also the breaking circle billiard, so when the circle, then the boundary is moving. But actually, these variables are not good because in some sense, time actually plays a role in this case. Why? Because we need to know at which point the ball hit the boundary to know which energy is transferred to the ball. So just the variable a parameterization of the boundary and the angle are not good because we need in some sense to put time inside the map. And then just let's try to reconsider the fixed once again circle billiard, but from another point of view. And then the first thing that we can think is that, okay, we have that the first integral that we already commented are the normal, the velocity, and the angle of reflection. But then also the energy, let's say the double, that we call A, we'll see that for some just technical reason we use double of the energy, and also the norm of the angular momentum are also first integral, so this is obvious. Actually, what happens is that the angular momentum is a first integral. It is preserved at every time. Actually, between two bounces, we have a free motion, and the angular momentum is clearly preserved in the free motion. Then the idea to introduce time in a map that describes the billiard motion is to use a map that has the angular momentum, norm of the angular momentum as a parameter, and with variable we use the time of impact and the energy. Then actually it is very easy to, once you have the angular momentum and the energy, to recover the trajectory, because from here, from the relation defined with the angular momentum, R is no, this is no, the velocity is square root of the energy of A, and then you get very easily the angle of reflection, and you choose the sign depending on the sign of the angular momentum. Also here, what are the motions along the diameters are the one for which L tends to 0. And then if we consider, for example, L that tends to 0, that A is large, then the cosinus of phi must be small, and then we get orbit along the diameter correspond to L small. So this is just for what we are going to talk about later. Okay, so how can we define the map with this variable? Then we can define the map also easily with this variable, just in the same way as before, using elementary geometry. Then we have y, because the chord between the two impact times has this length, and then it is very easy to compute the time between two bounces just using the relation basis space over velocity, and just rewrite it in terms of the angular momentum that we fixed. And once again, in this case, we have in another case, it is also an integral map. So this map is basically the same phase space as the first one before, that we have seen before. So it is also twist with these variables. So the answer is no. Why? At least it is not twist for all values of a, because why? To be twist, we need the derivative of t prime to be 0. Then, but the derivative of t prime, the derivative of that function f that we have written before, but this function is not monotone. Actually, it has a maximum. What does this mean? This means geometrically that, recalling that this function f represents the time between two bounces, then this means that if you fix the time between two bounces and the angular momentum, actually there are two possible motion that satisfies this condition. So if you want to travel from here, you start here at time t0, then you want a bound, then you fix the angular momentum, you want the next impact after 5 seconds, let's say, then you have two possible ways to get it. It is just come from simple computation. And these two possible ways corresponds to two energies, that is a high energy, that is the solution with plus, and a small energy, that is the solution with minus. And this corresponds to two different angles. But since we have seen that this function is monotone, for example, for A large, then this this indeterminacy is resolved just choosing the solution with higher energy. So this is a hint that suggests us to work only with very high energy. And this we will use it later. What about the generating function? Then the generating function, also in this case, the map is integrable, then the generating function can be computed explicitly. Actually, for maps with this form, the generating function can be computed explicitly just using this formula here. Then the generating function is the one just has to compute a primitive or the inverse of the function f, and then we have the generating function can be written in this way. Then actually this is defined for a very large. Remember that we were working with high energy. And then in our case, just after some computation, we get this explicit formula for the generating function. That actually is much more complicated with the one that we use in the other case with other variables. Okay, so going on, the question is, okay, why have we spent so much time in try to find and try to use the generating function? The idea is that because the generating function allows to enter inside a variational formulation of the problem. That is, if you have a diffeomorphism that can be expressed through a generating function like here, then given an orbit, you have that this relation is fulfilled. Actually, this is a if and only if. Then it means that orbits can be seen are in one-to-one correspondence with solution of this difference equation.
Yes, it's okay.
Yes, okay. So we had the variational approach that says us basically that Aubry-Mather theory tells us, given some hypothesis on the function, on the generating function h, we get a lot of information on the orbit. So the idea is to find a generating function for the billiards with moving boundary. That is our case. So what happens is that in this case, the first integral that we had before, where the energy and the angle of reflection are no more first integral. Actually, at a bounce, you get a transfer of energy. But what remains is that the angular momentum is still a first integral. This basically only depends on the fact that the tangent component of the velocity at the bounce, that is this one, is preserved. So the idea is to describe the dynamics for a fixed angular momentum with the variable time and something related with the energy. It will not be exactly the energy, it will be something related to it. So let us start just what we did in the previous case, that is to study the Dirichlet problem. So fix the two times of bouncing and try to find the solution that satisfies the Dirichlet problem. So the Dirichlet problem is exactly this one. We have the free motion between the bounces. We have to stay inside the circle at every time, and then we have a bounce that is given by the bouncing condition is just this one. And the idea is to study this motion in polar coordinates, fixing the angular momentum, and then we get the classical motion in polar coordinate. This is the conservation of angular momentum, and it's given here. Then what matters is the radial component. And if you recall, if you remember, in the first case, in the non-fixed case, we had that this Dirichlet problem adds two solutions, one with high energy and the other with low energy. And actually the same happens in this case. So what happened in this case is that fixing the energy, fixing the angular momentum, in general, we have two solutions to this problem. But we can distinguish between the two, choosing the energy very high. The energy very high means that the time of travel between two bouncing is low. Then if we choose this, if we fix the high energy, or in this case is the time of travel between two bounds very slow, then we find just one solution of this problem. And this solution enjoys the property that is written here. That what does it mean? It means this property here means that actually we have somehow a proper bounce. That what happens that when we bounce in the idea is what happens just after the bounce. So it means that we hit the boundary and then the ball is somehow going away from the boundary. So in principle, it would be possible that the ball hits the boundary, and if the boundary is expanding, the ball hits it and then in some sense continue to follow the boundary. But this is not possible, and this is said by these two conditions. And the same what happens just when we hit the boundary. So we are hitting the boundary going towards the boundary itself. So what we have is that we have proper motion. So if this is the boundary, if this is the ball, we have this kind of motion, bounces. We don't have this. And neither we have this. So this is also intuitive if we think that we are working with very high energy. If we are working with very high energy, we hit the boundary and we go away. This is just the meaning of this condition here. So the idea of the proof is just to solve the Dirichlet problem. Then this is an explicit solution. Then we have just imposed the boundary condition.
Can I ask a question?
Yes.
I don't know how to write it. So if you go back to the previous slide where you were seeing these two scenarios, imagine that you hit the boundary and then you reflect away from the boundary, but the boundary is moving, so the boundary catches up, like follows you. And
no, it cannot, because we are the idea is that it cannot happen because we are moving at very high velocity.
Okay, so it's the high energy avoids.
So, exactly. The idea is that we have two solutions. We have two solutions, one with high energy, the other with low energy. And we always choose the one with high energy just to prevent these things to happen.
So high is depends on what the boundary motion is. Once you figure
yes, in some sense, the boundary. So the motion is periodic. Then the velocity of the boundary is finite. Then we are always working. We always suppose that the ball is moving very fast. This is what we are trying to do. Okay. So the idea, actually, just to answer your question, is that here we have a solution that depends on A, that is the energy, and actually, imposing the boundary condition, we have two possible values for the energy, that has one with high energy, the other with low one, and the one that satisfies the condition is the one with plus, so the one with high energy. And then looking at what happens when the boundary was frozen, we had that the energy that gives the good solution is this one, and then what happens is just we have the values of the radius. If it's fixed, here splits in two. There is a time where we corresponding to the time of bouncing before and after. So the idea is, can we use the solution to different Dirichlet problem to build a true solution that is to glue them together? And actually, the answer is no, because the bouncing condition is not, in general, it is not guaranteed. And then the idea is to use, to find a good sequence of impact time. That is, what we're going to show is that we can find a method to find a good sequence, so that if the impact time are the ones coming from this sequence, then the bouncing condition is automatically guaranteed. This idea actually goes back to Moser and introduced it for in the case of ODEs, that he was thinking about concurrent maps, and also was used by Kunze Ortega in the study of the Fermi-Ulam model. So the basic idea is to define the function h, that actually will be our generating function, to be the action between two impact times. evaluated along the solution that we found in the Dirichlet problem at the beginning. So the Lagrangian is the reduced Lagrangian, because we saw that the only thing that matters is the radial component. And what turns out is that making some kind of computation, that is just computing the derivative with respect to t0 of this function, we get, just using some trick of integration and implicit differentiation, we get that the derivative of those functions with respect to the first variable is the one given here. That actually is, let's say, the energy plus something modified. This is the derivative with respect to the first variable. What happens if we, and it is copied here, what happens if we make the same with respect to the second variable? Then we have a formula that is the analogous to the first one. Then if we suppose to have a sequence of time that satisfies this relation, that is, if we see these two functions here are more or less the same, changing the sign and shifting in time. But then if we take, for example, the second one, that is this one, and we shift one back in time, and we suppose that the sequence satisfies this relation for every time, then what do we need? We have to equal this one that are now at the same time. These two values are the same, that they cancel out, then we get this relation here. We can complete the square, and then remember that we are working with high energy, then we can get rid of the squares and choosing the right sign. And what turns out is that if we have a sequence of time that satisfies this relation here, then automatically the bounces condition is satisfied. So what can be proved is that actually, if we have a sequence of time Tn that satisfies that condition that we saw before, and such that the difference is small, then we have a solution to the Dirichlet problem. And to this time we choose the radial velocity coming from the solution of the Dirichlet time, then we have, actually we can define a bouncing solution. Why? Because we have from r dot, we have the radial component of the velocity, and from the values of the radius as time Tn and the angular momentum, we have the tangent component of the velocity. Then we have the time of impact and actually the velocity vector. Then from this we can actually build a complete motion. Then we saw that this function h is very important, and it can be computed explicitly and has this formula, this expression here that is very similar to the one that we had for the frozen case, and also enjoys this property that we have here. And it is defined only in a strip. Then we have that is a reminiscent of the fact that we are working with high energy. It is C2, it is periodic in this sense. The mixed derivative has definite sign in the strip. And this is, if you recall, that is something that resembles twist, and then it is a definition of generating function. And the partial derivative with respect to the first and the second variables are this one. Oh, here maybe there is, yes, are this one. And then this gives us, recalling the definition of generating function, to choose a new variable that is actually the variable k, that is this variable here. Why? Because if you choose this variable as a new variable k, this one, then we can define implicitly this diffeomorphism. So this is just the derivative with respect to the first variable. The action is of the h, it would be the generating function in this one, that is k. And then we can define diffeomorphism implicit in this way. This definition is well defined because the mixed derivative with respect to the two arguments have a definite sign. Then we can invert it. Then actually this relation here defines implicitly a diffeomorphism. And what turns out is that an orbit of this diffeomorphism defined here corresponds exactly to a bouncing solution. Why? Because from the value of k, that is this variable here, we can recover the value of the radial velocity here. Then an orbit of this one, of this diffeomorphism, corresponds to a solution, to a bouncing solution. And then what happens is that actually what we have found is a generating function of the billiard map for our case. And it is explicit in the sense that it can be written in this way. So we are now ready to try to apply the Aubry-Mather theory. Then what does Aubry-Mather theory say, the general theorem? It says that if you have a diffeomorphism of the whole cylinder that has a generating function, and the generating function satisfies this property here, that are exactly the one that we had before, more or less, then, here is R2, no, not R, sorry. Then we can find several invariant set that we call M omega, for every omega that is the rotation numbers, such that if the omega is rational, then the sets contain periodic orbits, and if it is irrational, then the set is either an invariant curve or a Cantor set. And moreover, each orbit on this set satisfies this kind of estimate. That actually is something that we will use to give an estimate on the shapes of the set M omega, also the location in the phase space of the set omega. Then we want to apply this theorem to our case. The function h that the billiard map actually satisfies. This is just a sketch of what happens. So this is an integrable map in which we all have the orbits are actually invariant curve. Then in the general case, what happens? The curve with the orbits on the curve with rational omega are transformed, let's say, periodic orbits survive, that are this one, while if you take the irrational case, we can have either invariant curves or Cantor sets. So this is just a picture of what the Aubry-Mather theory tells us. So what we want to do is to apply this theorem to our map. But the fact is that our map, the generating function of the billiard map satisfies all the properties, apart from the fact that they are satisfied not on the whole R2, but only on the strip. So we have that our generating function is defined only on the strip. And it means in the cylinder that our map is just defined on the top of the cylinder, let's say the upper part. Then to apply the theorem, we should extend everything to R2. See that once we extend the generating function to R2, we are extending also the diffeomorphism to the cylinder, but extending this part here, we are modifying the cylinder also here at high velocity. Then find the invariant set for this modified map, and then consider only the orbits, that is the invariant sets that are contained in the red part, because the red part is the one that corresponds to the billiard map, let's say. Here, the blue part and the red part is something auxiliary that doesn't have nothing to do with the billiard map. This actually can be done, and this is the strategy, actually to extend the generating function to the whole cylinder, find the mother set for the modified generating function, recall the estimate that we had before on the distance between this one, between the T1 and T0, and recall that this can be bounded just by the rotation number, and note that this, if for all n this is satisfied, then we have that the mother set for the modified map are the one that we have. So it means that we are in the red zone. Actually, this plan works if we require that sigma that is wide and is sufficiently large, and this is just we see that sigma can be actually computed explicitly, and this gives the definition of the class R that we had at the beginning. So the class R is the set of functions that satisfies that sigma is greater than 2, where sigma is this one here. So it is quite ugly to see. And then we get the precise result of periodic and quasi-periodic motion, that is this one. We have fixing the angular momentum not so large, then we can find some frequencies that corresponds to either periodic motion or quasi-periodic, and the definition is here. I don't want, just for lacking of time, I'm not going on this point, because actually this is curative, and I would like to pass to the chaotic case. So how can we prove chaos? The idea to prove chaos is just to use some theory for exact-simplected Twix maps that actually says basically that if the Mather set with irrational rotation number is not an invariant curve, then we have chaos nearby. And the idea is that actually what we will use is this result of Forni. There is also another result by Angela, but we will use this one. Actually, we say we have that if the Mather set with irrational rotation number is not an invariant curve, that it is a counter set, and close to that counter set, there exists some invariant measure that has positive entropy. Actually, this is the result before that we are trying to use. So the idea is, how can we destroy invariant curve? So how can we find a method to destroy invariant curve? And the idea is to use, once again, a characterization of invariant curves that is given by Mather. The Mather says that if you take actually the second variation of the action, it can be written in this way, and you evaluate it on an invariant curve, then you have a positive number. Actually, if you define this function, that is actually the second variation of the action on the invariant curve, is always positive. This actually is written in for a sequence of time, let's say for the generating function, sorry. But this function can be also be defined in the cylinder, and it means that it can be written this way because xn plus 1 it can be seen as a function of xn and yn. Then in the cylinder you have the function defined here in this way, just writing xn minus 1 and xn plus 1 as a function of xn and yn, must be positive if xn and yn stay on an invariant curve. So how do we want to apply this to the billiard map? So the idea is, once again, extend the map to the whole cylinder. Then, to find some time t bar such that our function a that we have defined over there as a function of t and k that is defined on the cylinder is negative for this value t bar and for an interval of k. This means that we can detect in the cylinder a vertical segment that acts something like a wall. It means that invariant curves cannot cross this wall. So in some sense, we build a wall here, and it means that invariant curves can actually go close to this wall, but they cannot hit them. Then to find an invariant, then to find a rotation number corresponding to an invariant curve that cannot exist, the idea is to find a rotation number for which an invariant curve with that rotation number must hit the wall. Then it means that the Mather set corresponding to that number is actually a counter set, and then we have chaos. How can we do this? First, we have to compute this function a, and this function a can be computed easily if we work with small angular momentum. This is why at the beginning I was telling you that small y, and I was insisting on something with small angular momentum. So if we have small angular momentum, this function a can be computed in this way. Then to make it easy, we consider a point that we have freedom to choose the t bar, that is the location of the wall. Then we choose a point in which r dot, it is periodic, is 0, so we get rid of all this part. And writing it in the cylinder, we get that this function has this formula here that we get, once again, we put here. Okay, so we have found a point at t bar where we should put the wall, and then we have also to decide how tall this wall can be. And then we need this function to be negative, but then here we have k. Then it is easy to see that this function is negative if we take L small, just to get rid of this reminder, and we choose k between these two numbers. So this is very easy. But actually this is a too large interval because we are working with very high energy. It means that k cannot be 0. Then the equivalent of asking T1 minus T0 less than sigma is just to ask k greater than this number. And then we can choose k where in this interval, provided that this is actually an interval. So we have this one, this condition. This condition here is just gives the fact that this is less than this, and then we actually have an interval. So what we have built the wall for the billiard map. Now we have to find a good rotation number such that the possible invariant curve with that rotation number must hit the wall. And then once again, to do this, we use the usual estimate that gives an estimate on the, let's say, the oscillation of the curve in terms of its rotation number. And what can we prove is that if you have rotation number, invariant curve with rotation number omega, then in the phase space, the curve is bounded by two numbers. And here is L, it is not C, sorry, by two numbers that depends on omega that are this one. With the figure, what can we say is what we have here. We're almost done. We have that if you have an invariant curve with rotation number omega, then it must be contained in this part of the cylinder. And then what we want is that we can just plug this part of the cylinder in the zone when there is the wall. Then it means that an invariant curve with this rotation number is forced to hit the wall. Then it cannot be an invariant curve, and this must be a Cantor set, and close to the Cantor set we have positive entropy. Then what we need is that these four numbers here are ordered in the right way, that is exactly this condition. So the final technical lemma is that if the function L satisfies this very ugly condition, actually we can find an open interval of rotation number omega such that this condition is satisfied, and then such that the corresponding invariant curve must hit the wall. So what we have is that to these invariant curves we can apply the result of Forni, and we have many invariant measures with positive entropy close to those Cantor sets. Then, just to state formally the second result, and we are done. Then the class R tilde is just defined by the set of the function RT that satisfies all these conditions that are the ones that we have been introducing so far. And we can prove that this set is not empty, and actually there is a sinusoidal function can stay here inside. And what we have is that for function, for radius that are moving according to function in R tilde, we have this result here that is actually the formal result that we can prove is that if we have, just let me state this, if we choose a radius that stays inside this function of R, then we fix the angular momentum sufficiently small, then the billiard map with that angular momentum actually has positive topological entropy. In particular, it is not only positive topological entropy, but we can find actually many invariant measures that has positive entropy. This for each angular momentum that is sufficiently small. So this is actually the idea of proving the result. So the basic ingredient is, just in a word, to break invariant curve. So the fact is, for integral twist map, that is maps that are defined through a generating function, if you're able to destroy invariant curve, then you get chaos. And the idea to destroy invariant curve can be more or less difficult according to the problem. Here in this case, we had a problem given by the fact that the generating function is not defined on the whole R2, and also that we are working with high energy, but it means that tau 1 minus t0 is very small. Actually, the generating function is defined on a very thin strip of R2. So, well, this was the idea of the result that I would like to show you. And just sorry for the technical inconvenience that I had before. So, thank you very much.
So thank you for the very nice talk. So if there is any comment or question, we have time for questions.
I can ask another question. If you go to the previous slide,
Which one? This one?
Yeah, this one. So you talk about these invariant measures with positive entropy.
Yes.
do you actually have measures that achieve the topological entropy, like measures of maximal entropy? And if so, are they unique?
Yes, they're uniquely ergodic.
So these measures have just positive entropy or positive entropy equal to the topological entropy?
Oh, these I don't know. Sincerely,
Some intermediate positive entropy, but not necessarily equal to the maximum.
I don't know.
Okay. Because it would be interesting to see if you can find a measure that actually achieves
yes, I see. Yes, I see what you have.
The upper bound by the
Exactly. This I don't know. I think that one should. Yeah, actually, this comes actually from the result by Forney, and I don't know if here what we are doing is just to apply that result. Actually, I don't know if the variant measure that he found that you find are actually the one that you are talking about. I don't have the money. So.
Thank you.
Any other comments? So I have a question too. So in this case, what you do, you take the circular billiard and then you make some rescaling. I mean, the shape will remain the
exactly.
same. So so I guess you can do the same for other shapes, not the circular one, but then the problem is that it's also important the point where you start on the billiard, right?
Yes, but one can think about it, but the big problem is that the only shapes for which the angular momentum is preserved is the circle.
Yeah, but so also I think if you start from a non-circular billiard, then also the point where you start.
Yeah, sure. Yes, the idea is that in this case.
The question was, sorry, can you do the same if you take a fixed circular billiard, but then you define the way to reflect at every point in a periodic way? So you just change the reflection law at every point, in a periodic way. So being fixed in a circle. So I don't know if it's the same model or maybe similar.
Yeah, the idea can be, so you should in some sense find new variables in which the billiard is fixed and see what happens to the map.
Yeah, I'm just saying you just change the reflection. It's not elastic anymore, but probably it's the same. I mean, it's a similar class of system because in this case you are also changing the reflection somehow.
Yes, but yes, I think it could. Yes, one has to find actually which is the exact relation between the two. So yes, I think that something can be done. The idea is that always just depends how you can define a generating function for this kind of system. Maybe also with this trick for the action works. So I don't know if the problem that you are proposing is exactly equivalent to the one that we are.
No, maybe it's not equivalent, but it's very similar, I guess.
Yes, it's very similar. So the fact is to define a generating function. Then
in your case, also the distance between boundary points is increasing because the billiard is moving.
Yes.
I was suggesting the distance is fixed, but so the velocity is fixed, but then the reflection is just different. Anyway.
Yes. So the important stuff is to find to define a generating function so that it works, and I think it can be tried just with that kind of trick.
If I can add just a comment, I mean,
sure.
If you do it, with respect to your question, Alfonso, if you do it in a very general way, I think that in principle, you don't preserve the angular momentum. So the system becomes with many more degrees of freedom, and you go to higher dimension, and it becomes more difficult.
For a generic shape.
But if you preserve
if you do it in generic, I mean, if you for a generic law of bouncing, I mean, you can do it. If you still preserve the angular momentum, then probably it's the same. It's very.
Yeah, but maybe if at the boundary you preserve the tangent direction of the velocity, this should imply that you're preserving angular momentum, right?
Yeah, probably.
So the idea also should be to change the radial impulse should depend on time, for example.
Okay. So, is there any other comment or question?
Another option would be to keep the radius of the circle fixed, but then have the center of the circle move slightly, let's say on a tiny circle. So you would have a kind of wobbly circle, but the circle stays the same.
Yeah, I think also.
So that would be another small perturbation of these classic systems. Okay.
Yes, also, just the problem is that in this case, at every bounce, the impulse is only given in the radial direction or not?
So dancing billiards rather than...
Yes, it's kind of dancing billiard.
Okay, so if there is no other comment or question, so let's thank Stefano again.